At ang iyong pumping mode, ang discharge niya ay 44.8 and 48.7 cubic meter per second. Okay. So sa magat naman, okay, if you're going to take a look, so meron tayong capacity, no? So yon. Okay. So installed capacity is 360 megawatts. Okay. Meron tayong average annual output na 929 gigawatt hour. Ang dam height natin is 114 meters. The rated net head is 81 meters. Okay? Ang rated flow rate niya, take note, 128 cubic meter per second per unit. And they are using 4 Francis units. Merong capacity na 90 megawatt each unit. Okay? So, yan yung specifications ng ating Magat Dam. Okay. San Roque, no? Meron naman tayong 200 meters tall na dam, 1.2 kilometers long embankment dam coming from Agno River. Okay? So, dito, we could have our installed rated capacity of 345 megawatts. Okay? It says here that it operates primarily as a peaking plant during periods each day when the electrical output of the base and intermediate load power plants cannot fulfill consumer demand. Kaya sabi ko sa inyo, mostly they are they are operating as peaking load power plant. Okay? So capacity of 85 megawatts, which is the basis for the capacity payments. And then in the Pulangi, no, we have the generating capacity of 255 megawatts or equivalent to 342,000 horsepower. Okay? Meron tayong estimated flow rate, no? So 1,500,000 cubic meter. Okay? So yan yung ating requirement, okay? To run your hydroelectric power plant. Okay? And then the Angat Dam, okay? We have the water level of 210 meters. Okay? Ang dam niya is 131 meters high and impounds water from the Angat River. Okay? So dito nanggagaling yung or even in the lake. Okay? So yung requirement nila, no, to run the hydropower plant. Okay? So ano yung mga type ng ating hydroelectric power plant? First is yung pump storage, no? Run of river and impoundment facility. So paano ba yung ating pump storage? Sabi ko nga, there are 2 modes involved. One is yung generation of electricity. So ibig sabihin, turbine operation. Pump turbine ang tawag sa kanya dito. Okay? Kasi dalawa yung kaanyo niya. Dalawa yung kanyang mode. One is nag-generate siya ng electricity. Ibig sabihin, it acts as a turbine. Kapag ka naman nag-i-store siya ng electricity or basically it stores water, okay, pump yung nag-ooperate. It operates as a pump. Okay? So dito, pababa yung water natin flowing through the penstock at tumatama dito sa ating hydraulic turbine blades. From the upper basin down to lower basin. Okay? So it produces energy. It produces water power. Meron tayong electrical power output dito. So this is basically generation of electricity. However, kapag storage naman, no, mapapansin mo, it acts as a pump, no? So from the lower reservoir, ipapump mo siya going to upper reservoir para i-maintain mo yung level ng water at the upper basin or upper reservoir. Okay? So, ibig sabihin, nag-ooperate siya no, as a turbine, nag-generate siya ng electricity. Kapag ka naman nag-ooperate siya as a pump, it stores water no, galing dun sa iyong lower reservoir paakyat uli. Kasi nga, hindi mo pwedeng pabalikin yung tubig no, dito kasi merong certain elevation without using a pump. So, yung pump mo acts as a, yung turbine mo acts as a pump no, during storage. Ang tanong, pwede bang sabay sila? Pwede bang magkasabay yung power generation at saka yung storage ng water? Hmm? Pwede ba siyang magkasabay, Agila? Agila, J-Lo. Pwede, bakit? Paano mo nasabing pwede? Paano? Paano mo nasabing pwede? Paano nasabing pwede? Agila, Agila. O kaya nga, ang tanong nga, pwede ba sila magkasabay? At the same time, nag-generate ka ng electricity at the same time, ikaw ay nagpapump ng water from lower to upper reservoir. Paano? Balikan natin ito. Okay? So, kita mo ito, bumababa dito ang tubig. So, by gravity siya. No? Ito naman, you need power input. Ibig sabihin, kapag magkasabay sila, no? During operation, no? Yung nagge-generate ka at the same time, nagpapump ka. So, part of the energy that is being produced is used, no? As a power input sa iyong pump. So, pwedeng pataasin mo yung tubig at the same time. Okay? So, simultaneously, no, you can do both or you can set yung parehong mode niya, generation and storage. Okay? So, ganyan kapag pump storage ang tawag sa kanya. Yung setup. No? So, meron tayong elevation dito. No? Yan yung tinatawag nating height. Okay? Or head. Okay? Pag nag-pass through naman yung water through the penstock, okay, we can measure its velocity, the reason why it develops potential energy, kinetic energy rather. Then after that, kinetic energy is converted into rotational energy or motion kapag tumama yung water mo dun sa blades ng iyong hydraulic turbine. Okay? So pump storage power plants are able to react within short period of time to network fluctuations by generating the required electricity or by absorbing any excess. Okay? Modern system need just 30 seconds to start the pump, take note, or turbines up from a standstill. In the event of power failure, pump storage plants can re-establish the power supply to the network without an external energy supply. Okay? So, grid stabilizing services of pump storage, we use it as a backup and reserve power. It could respond to emergency situations. Likewise, we have your quick start capability, which provide power within shortest time to grid, and black start capability, which is the ability to restore power system after blackout. Regulation and frequency response, active power regulation. Likewise, we have voltage support. Reactive power regulation is spinning reserve. Okay? Another type is yung run-of-river hydroelectric power plant. Okay? So, paano naman siya? So, these are small hydro. No? Kapag pagka pump storage, no, large hydro siya, malalaki yung megawatt output niya, megawatt capacity. However, for run-of-river, okay, so these are considered small hydropower plant. Large hydro dams are costly to build, and new facilities require extensive timelines of consultation, planning, and regulatory requirements. Okay? So, dito sa ating run-of-river, okay, these factors propelled small hydro into energy sink. Okay? Makikita natin dito na there's no such dam to be built. No? As long as meron tayong at least minimal, no, elevation or head, no. Okay, sabi nga dito, there is an elevation change, no. A run-off river is actually a diversion strategy that redirects part of a downward flowing waterway through a pipe down the head to spin turbines and generate electricity at a lower power. Okay? So, tatama mo lang dito. No? Kaya nga run of river. No? So, once na tumama dito yung water mo, dumaan siya dun sa penstock mo. No? Iikot na directly yung water. So, continuous lang yung supply ng water natin. Okay? So, meron lang tayong ginagamit na 4B. Okay? So, maliliit lang. No? Maliliit lang yung capacity kapag run of water. Okay? So, cleaner, of course, yan ang one of the main advantages of your hydro. Cleaner power, fewer greenhouse gases. Like all the hydroelectric power, run of the river hydro harnesses the natural potential energy of water, eliminating the need to burn coal or natural gas to generate electricity needed by consumers and industry. Okay? Less flooding, of course, yung reservoir. No fuel required. No? Water lang ang iyong medium. No? So, yung water natin serve as our renewable source of energy. Okay? Cost of electricity is constant. Okay? No air pollution is created. Of course, long life, okay, of the plant. Okay? Kasi kung sasabihin natin, kung i-compare natin sa thermal power plants, no? The hydroelectric power plant has a longer life, no, than the thermal power plants. Okay? There are some hydroelectric power plants that were built more than 50 to 100 years ago and are still running. Okay? Of course, yung cost of generation of electricity, yung production cost natin, no, mas mababa compared with other thermal with the thermal power plants. Okay? Can easily work during high peak daily load, so kaya nga siya ay considered as a peaking load power plant. Okay? So the peak power, of course, at night, obviously during night time, you generate more electricity. Ibig sabihin, kung ikaw ay nag-ooperate in a pump storage hydroelectric power plant, generation of electricity is done during night time. And syempre, siguro yung storage, no? Kung hindi mo pagsasabayin yung iyong uh, mode, no? Storage can be done during daytime. Okay? So of course, the use of dams natin, no, to, to, to impound water. Okay? So meron tayong ginagamitan ng mga irrigation system. No? Yan. So these are some of the disadvantages. Merong unfirm power. Okay, run of the river power is considered unfirm source of water. A run of the water river project has little or no capacity for energy generation and hence cannot coordinate the output of electricity generation to match consumer demand. So, ibig sabihin, mababa lang yung na-generate natin, particularly kapag run of the river. Okay. Emission, no? There are some sort of emission din, okay, of methane and carbon dioxide during the process. Okay. Disturbance of habitat, of course, installation cost, okay, and the limited use, divert natural waterway, effects on agriculture, okay, and fish killing, dispute with people and breaking of dams and availability of sites. Okay? Ngayon, sinasabi natin, kung ikaw ay magtatayo ng isang hydroelectric power plant, no, where are you going to locate it? No? So there should be a river, there should be lakes, no, that could be sufficiently provide the amount of water required. Okay? So here, isa nating dinedesign pag pag di-design ka ng isang power plant ay yung type ng hydraulic turbine. Okay? So yung hydraulic turbine na gagamitin natin dito, okay, which serve as our prime mover. Okay? So what are the parameters needed and what are the design considerations? No? So storage power, hydropower offers a big advantage over many other energy producers that can respond to increases in demand almost immediately by relaxing extra water, which spins the turbines faster and generate more electricity. Okay? So obviously, so ito yung ating dam. This is a concrete structure. Okay, and then the reservoir, the upper reservoir. Or ito na yung ating lower reservoir reserve. Ito na yung ating river which serve as our lower reservoir. Okay? So dito, we define dam as the most important component of the hydropower plant. Okay? So it's built on a large river that has abundant quantity of water throughout the year. It should be built at a location where the height of river is sufficient to get the maximum possible potential energy from the water. Okay? So the water reservoir is placed behind the dam where water is stored. Okay? The water in the reservoir is located higher than the rest of the dam structure. Take note, the height of water in the reservoir decides how much potential energy the water possesses. Kasi nga sabi nga natin, your potential is energy is a function of the height of water or the heat, yung elevation natin. mg, z, or h, no, yung height ng water. Kaya doon natin ma-measure yung potential energy. The higher the height of water, obviously the more its potential energy. The high position of water in the reservoir enables it to move downward effortlessly. So, ibig sabihin, by gravity, babagsak yung water, magpo-flow dun sa iyong penstock, no? Diretso lang, no? By gravity. Okay? The height of water in the reservoir is higher than the natural height of water flowing in the river. So it is considered to have an altered equilibrium. It helps to increase the overall potential energy of water, which helps ultimately produce more electricity in the power generation. Intake or control gates, ito yung sinasabi natin na these are built, no? Ito yung nagko-control, okay, ng flow ng water punta sa penstock from the reservoir to the penstock. Okay? These are called inlet gates because water enters the power generation unit through these gates. When the control gates are open, the water flows due to gravity through the penstock towards the turbine. The water flowing through the gates possesses potential as well as kinetic energy. So penstock, this is a large diameter pipe, a long pipe, okay, which carries water flowing from the reservoir towards the power generation unit. Okay, comprised of the turbine and generator. The water in the penstock possesses kinetic energy due to its motion and potential energy due to its height. Of course, itong water turbine natin, iba-iba yung gagamitin nating water turbines or hydraulic turbines. Examples are Kaplan turbine, Francis turbine, Pelton wheels. Okay, so these are commonly used, no? Hydraulic or water turbines for hydropower plant. So they differ mainly doon sa configuration ng ating or blade geometry. Meron tayong tinatawag na blade geometry. Magkaiba yung configuration kapag Kaplan, kapag Francis, o kapag Pelton wheels. Okay? So the type of turbine used in the hydropower plant depends on the height of the reservoir, quantity of water, and the total power generation capacity. So ibig sabihin, you have to select, no? Kapag nalaman mo na yung mga height ng reservoir, quantity ng water, and the total power generation capacity, you can select the appropriate type of hydraulic turbine. No? So meron tayong table later that will be the basis on how you are going to select your turbine, no? Given the specific speed, given the head or height ng reservoir, and then of course yung ating operating speed. So yan. So these are the complete. Ito yung diniscuss natin. So naririto yung control case. This is considered a your penstock. Okay. These are the reservoir. Okay. This is your hydraulic turbine. This is your dam. So ano yung sizes ng mga hydropower plants natin? Meron tayong considered as a large hydropower. It has a capacity of more than 30 megawatts. No? Small hydro, nasa range siya ng 100 kilowatt to 30 megawatt. And micro hydro, no, up to 100 kilowatt. Okay? So ngayon, meron tayong tinatawag flow path. No? Paano ba nagpa-pass through yung water doon sa iyong hydraulic turbine? Ano yung flow characteristics niya? Okay? So doon sa flow path natin, we can categorize three types of hydraulic turbines. First is yung axial flow, no? Hydraulic turbines. Example of which is Kaplan. Then of course yung radial, no? So sabi nga dito, kapag axial, siya ay parallel, the liquid. The flow path of the liquid is parallel to the axis of rotation. Okay? Liquid flow mainly in axial direction. Kapag naman radial flow hydraulic turbines, no? It has the liquid flowing mainly in the plane perpendicular. No, perpendicular naman siya doon sa axis of rotation. Then pwede rin mixed flow, no? Nung radial at saka nung axial, no? Best example of which is the Francis turbine. Mixed flow type siya, no? Sabi dito, Francis turbine, water enters in radial direction and exit in axial direction. No? Based naman sa pressure change, meron tayong tinatawag na impulse turbine. The pressure of liquid does not change while flowing through the rotor of the machine. And impulse turbine pressure change only occur in the nozzle of the machine. Okay. Example of which is a Pelton turbine. No? So later, ibibigay ko sa inyo yung performance parameters ng isang Pelton turbine. No? A Pelton turbine has one or more bridges discharging water into an aerated space and impinging on the buckets of the runner. Okay, so there are drop tubes are not required for impulse turbines since the runner must be located above the maximum tailwater to permit operation at atmospheric pressure. Then meron tayong turbo. This is a variation. Variation siya ng Pelton. Turbo runner is a cast wheel whose shape generally resembles a pan blade. So nakakita na kayo ng electric pan. So parang ganun. Pan blade that is close to the outer edges. Okay, the water is stream is applied on one side, goes across the blades and exits on the other side. And then meron tayong cross flow turbine. No? This is a drum shape and uses an elongated rectangular section nozzle directed against curved vanes on a cylindrically shaped manner. No? Meron tayong tinatawag na squirrel cage. No? It resembles a squirrel cage blower. Okay? Second is yung reaction turbine. The pressure of the liquid changes while it flows through the rotor of the machine. Okay? The change in fluid velocity and reduction in its pressure causes a reduction on the turbine blades. Okay? Francis and Kaplan turbines fall in the category of reaction turbine. So, Francis turbine, ito yung kanyang hitsura ng blade. No? So, water strikes the edge of the runner, pushes the blades, and then flows towards the axis of the turbine. Okay? Sa Kaplan, ganito naman, similar to propeller turbine, except its blades are adjustable. Position can be set according to the available flow, and the turbine is therefore suitable for certain run-of-river generating stations. So yan yung hitsura ng blade, or this is the blade geometry for Kaplan turbine. And then of course yung propeller turbine. So simple lang siya. No, they can reach very high rotation speed. Propeller turbines are effective for low heads. So yun ang pinagagamitan niya. This is suitable for run of water power station kasi low head nga lang ang requirement natin kapag ka run of river power stations. Okay, usually they are using propeller turbine. So these are, yun nga, sinasabi ko sa inyo, how to select the appropriate type of turbine. No? So meron tayong specific speed. So this is in terms of RPM, range ng head natin, effective head, no? In terms of meter, and range ng runaway speed, which is RPM. Okay? So, pagka specific speed, pagka Kaplan, it ranges from 300 to 1,000 RPM. While the range of head or effective head for Kaplan is from 4 to 40 meters maximum. Okay? Pag Francis naman, meron tayong 50 to 450 RPM na specific speed. And 30 to 450 ano naman ang kanyang range ng head, effective head. Pag Pelton, 10 to 70. So, mababa lang yung specific speed niya. Pero mataas naman yung kanyang effective head. Cross flow, 20 to 70. Then, 5 to 200 meters yung kanyang effective head. And then lastly, turbo, 20 to 80, 30 to 300. So this could be a basis on how you are going to select the type of your turbine. No? So, syempre, magsiselect ka dyan. No? I-specify mo kung anong type ng turbine ang kailangan mo when you are doing the performance valuation. Okay? So, meron din tayong best efficiency. No? Pagka cross-flow daw, maximum is 80%. In turbo, we have 85%. So what are the performance parameters? Okay? So the difference ng total head for the water entering the turbine casing and the total head leaving the trap tube. Okay? So meron tayong net head or effective head which can be computed as Hg gross head minus your friction head loss. Sa friction head loss, gagamitin natin si Darcy-Weisbach equation. You can recall, this is a function of FLB squared over 2GD. Yung FD natin serve as your friction factor, L is length ng iyong pipe, okay? D is your hydraulic diameter ng pipe, B is velocity, G is your gravitational acceleration, FD is your Darcy friction factor. Okay? So kapag ka laminar flow, meron tayong approximate equation, no, that can be used to determine your friction factor. At for turbulent flow, no, you will be using Moody chart. Nakakita na kayo ng Moody chart, no, or Moody diagram, okay, to determine your friction factor. In the Moody chart, we have, of course, we should know how to determine your friction factor by having your values of Reynolds number and then of course yung roughness coefficient. Roughness coefficient is largely dependent on the pipe material used, no? So dinidefine natin kung alam natin yung roughness coefficient and then of course yung ating Reynolds number, then we can determine the value of the friction factor, no? Yan yung Moody diagram natin or Moody chart. Okay. Pero kapag ka naman siya ay laminar flow, okay, so siya ay pwedeng nating gamitan ng equation, no? We can use the equation for determining your friction factor, an approximate relation. No, mamaya bibigay ko sa inyo. Okay? So, your volume flow rate, of course, Q, no? Ito yung cubic meter per second, or cubic meter per R, cubic feet per second, no? Can be determined using continuity equation or vice versa, no? Given your Q, given your cross-sectional area, you can evaluate your velocity ng water. Okay? Volume flow rate. Okay? Ito yung continuity equation natin. Okay? Pagka naman inaano mo yung Pelton, which is your impulse turbine, examples of impulse turbine, your head natin, yung effective head natin is just a function of your pressure head and velocity head. P over gamma. No, specific weight ng water. Of course, you have your pressure. Okay? Velocity ng water. G. Okay? So, ito yung ating pagkuha ng ating effective head. Of course, meron tayong peripheral coefficient. Peripheral coefficient is pi dn over square root of 2g. Diameter ng runner, yung D. N is RPM. Square root of 2g is H is your effective head or net head. Okay? We can also compute water power using the English units. No? We have Q, yung volume flow rate natin. It should be in terms of cubic feet per second. Yung net head natin is in terms of feet. Density of water is pound per cubic feet over 550. The conversion factor para horsepower ang magiging unit ng ating turbine output. This is the water power, the turbine output. Pareho lang siya. We can also multiply it by turbine hydraulic efficiency. Turbine hydraulic efficiency. Or we can simply use for SI units Q gamma H. Yung H is effective head. Effective head is Hg minus Hf. No? Yung friction head loss, pag hindi ibinigay, or we cannot have sufficient data to compute your friction head loss using Darcy-Weisbach equation, we can assume na usually, yung friction head loss accounts for 10 to 15% of your gross sale. No? 10 to 15%, 1/5, no, of your gross head. So, ibig sabihin, if you have 10% friction head loss, no, so you got your net head, effective head of 0.9 of your gross head, no? So, yun yung magiging value ng iyong effective head. 0.9 of your gross head, meaning 10% of which is your friction head loss. Okay? So, for generator speed, we have N over 120 F over P, number of folds. No? Even number dapat ang number of folds, frequency, and angular frequency. Ito yung sinasabi ko sa inyo, one of the parameters that they can be used to select your type ng turbine. So this is NS, your specific speed. I-check dyan sa inyong manual, it should be NS. N square root of HP over H raised to 5 over 4. N is RPM, operating speed. Power ito, water power. Or it could be brake power. No? If your mechanical efficiency is equal to 100%, no? Then you got your effective head. It should be in terms of feet. Feet raised to 5 over 4. Pag naman SI unit, 0.2623 square root of kilowatt over H raised to 5 over 4. Meter naman, your power is terms of kilowatt. Ang NS mo is in terms of RPM, both. No? Both. Okay? Ah,
Yes po, sir.
okay. Baka hindi ninyo narinig ang audio. Tsaka hindi naririnig ang audio. Stop ko muna.
Kilometers per hour. That's enough water to fill about 100,000 Olympic swimming pools every day. Standing here, you can actually feel the power of the water. Harnessing that power is what hydroelectric stations have been designed to do for over 100 years in Ontario. In essence, they are factories that convert the energy of falling water into the flow of electrons, or what is commonly called electricity, the electricity that powers the province. Most hydroelectric stations use either water diverted around the natural drop of a river, such as a waterfall or rapids, or a dam is built across a river to raise the water level and provide the drop needed to create a driving force. Water at the higher level is collected in the forebay. It flows through the plant intake into a pipe called a penstock, which carries it down to a turbine water wheel at the lower water level. The water pressure increases as it flows down the penstock. It is this pressure and flow that drives the turbine that is connected to the generator. Inside the generator is the rotor that is spun by the turbine. Large electromagnets are attached to the rotor located within coils of copper wire called a stator. As the generator rotor spins the magnets, a flow of electrons is created in the coils of the stator. This produces electricity that can be stepped up in voltage through the station transformers and sent across transmission lines. The falling water, having served its purpose, exits the generating station to the tail race, where it rejoins the main stream of the river to continue the cycle of creating clean, renewable energy for Ontario.
Hydropower. Hydropower, or hydroelectricity, refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydro energy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator, which produces electricity when the turbine spins. There are two main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
Welcome to the video tutorials of Mekanismuller. This animation authored by Dr. Sehan Ersoy is the property of the client GDF Suez and subject to copyright limitations. We thank GDF Suez for giving us the permission to publish this video. There are three major types of water turbines. The Pelton turbine requires large water head and low flow rate, and the Kaplan turbines require low water head but large flow rate. The Pelton turbines usually build in mountainous regions, while the Kaplan turbines are located in lowlands. These restrictions make these two-kind turbines less common than the Francis turbine. The Francis turbine fills a large gap between the Pelton and Kaplan, and it is widely used. They operate in water head from 10 to 600 meters, and primarily used for electric power generation. Their power output can be calculated from the water head and flow rate and typically range from 10 to more than 700 megawatts. One of the distinct advantages of the Francis turbine with respect to other water turbine is that they can also be used as water pump. This makes them ideal for the pumped storage systems. This animation shows the operation of a Francis turbine in a dam. The arrows show the water path and direction inside the dam. The water from reservoir behind the dam transferred to the turbine by a penstock. The penstock diameter of a Francis turbine could be as large as 10 meters. The water coming from the penstock is transferred to the inlet scroll, which distributes the water equally around the wicket gates. Water passes through the wicket gates, which controls the amount of water passing through the turbine, before reaching to the runner. This in effect controls the power output of the dam. Wicket gates also adjust the angle of the water reaching to the runner. After passing through the wicket gates, the water reaches to the runner. The water pressure forces the runner to rotate. The rotation speed of the runner can be in the range of 80 to 1000 revolution per minute. The water continues its motion downward under the runner to the exit pipe. The exit pipe discharges the water to the environment as low-pressure water. The turbine shaft of the Francis turbines is almost always mounted vertically. This makes discharge of the water much easier due to swirling effect of the water in the inlet scroll, and the effect of the gravity. The rotation motion of the runner is transferred to an electric generator shown in here. The generated electricity is converted to high voltage current and transferred to the grid to be consumed. One big advantage of the water turbines is that power output can be regulated very easily. If the demand is reduced, the amount of water flowing to the turbine can be reduced relatively short period of time. We thank our client GDF Suez giving us the permission to publish this video. We also thank our viewers for their continuing support of our channel.
Time to go all out shopping. Enjoy these amazing deals at the Watson's nationwide sale.
The old water wheel is the precursor to modern Pelton turbines. Wood water wheels have been used to extract power from flowing water and convert it into mechanical power since the 3rd century. Often, water wheels provided power for water mills, which used millstones for grinding wheat to produce flour. The rotational movement of the water wheel spun the runner stone of the mill by means of a gear unit. The opening in the middle of the runner stone is called eye, where the grains were filled into. As the runner stone turned, the grains were being cut and crushed by the stones that turned the grains into flour. The water wheel has long been replaced by the Pelton turbine for several reasons. Because of their clever design, Pelton wheels are far more efficient than water wheels of the past. The rotational movement of the turbine is usually transmitted to a generator, converting kinetic energy into electrical energy. A series of spoon-shaped buckets is mounted around the edge of the Pelton wheel. Buckets are usually cast as one solid piece, which is necessary to avoid damage, such as fatigue failure. The buckets have splitters placed at the middle of them that divide the water jets into two equal streams. The divider splits the flow of water striking it and changes the direction of the water by almost 180 degrees. This allows the wheel to capture almost 100% of the water's energy. The water jet can reach speeds of up to 370 miles per hour, resulting in a very high rotational speed of the wheel. Pelton wheels can be operated with almost 3,000 rotations per minute. Pelton turbines can be installed horizontally as well as vertically. When mounted vertically, several nozzles can be employed, resulting in high turbine speeds.
Amazing deals at the Watsons nationwide.
Pelton turbines are suitable for power extraction when water energy is available at high head and low flow rate. Working of Pelton turbine is simple. High-speed water jet is ejected through a nozzle. When this jet hits buckets of Pelton wheel, it induces an impulsive force. This force makes the turbine rotate. In short, Pelton turbine transforms kinetic energy of water jet to rotational energy. The rotating shaft runs a generator and produces electricity. But demand of power may fluctuate over time. A governing mechanism, which controls position of spearhead, meets this requirement. With lowering power demand, spearheaded water inlet nozzle is moved in, so that water flow rate is reduced. If power demand increases, spearhead is moved out. This will increase flow rate. This in turn makes sure that turbine will rotate at a constant specified RPM, which conforms to the power supply frequency. So this mechanism acts as a speed governing mechanism of Pelton wheel. A cut is provided on bottom portion of buckets. This makes sure that water jet will not get interfered by other incoming buckets. One of the most important parameter of Pelton turbine design is number of buckets on the disc. If number of buckets is inadequate, this will result in loss in water jet. With lowering number of buckets, at some point of operation, complete water jet might be lost. This will decrease efficiency of Pelton turbine drastically. so there should be an appropriate number of buckets, which will make sure that no water is lost. Most vital component of Pelton wheel is its bucket. Buckets are casted as single solid piece, in order to avoid fatigue failure. Water jet is split into two equal components with help of a splitter. The special shape of bucket makes the jet turn almost 180 degree. This produces an impulsive force on bucket. Force so produced can easily be derived from Newton's second law of motion. Blade outlet angle close to 180 degree is usually used in order to maximize impulsive force. Absolute velocity of fluid will have huge drop from inlet to exit of bucket. However, pressure remains same. So Pelton turbine gains mechanical energy purely due to change in kinetic energy of jet, not due to enthalpy change. Which means Pelton turbine is a pure impulse machine. Pelton turbine design is always aimed at extracting maximum power from water jet, or maximizing efficiency. Power extraction is maximum when product of impulsive force and bucket velocity is maximum. If Pelton wheel buckets are held stationary, even if there is huge impulsive force, power extraction will be zero. Similarly, if buckets are moving with same speed of jet, water jet won't be able to hit the bucket, which leads to zero impulse force. Again, power extraction will be zero. In short, power extraction is zero, both at zero bucket speed, and when bucket speed is same as jet speed. So, optimum power extraction happens in between. It can be shown using Euler's turbomachinery equation that maximum power extraction happens when bucket speed is half the jet velocity. So it is always desirable to operate Pelton wheel at this condition. Pelton turbines can give efficiency as high as 90% at optimum working conditions. Hope you got a good understanding on working of Pelton turbines. Thank you.
Okay, nakikita ninyo itong slide ko.
Yes po, sir.
Opo.
Okay. So ito sinend ko na kay Justin para i-provide sa inyong GC. So ito yung discussion natin kanina, the Darcy-Weisbach equation, which is basically a function of your friction factor, the length of the pipe, velocity, squared over 2GD. Okay? So your FD can be taken from Moody diagram. Okay? Particularly kapag siya ay turbulent flow. Okay? So HF usually, sabi nga natin, is a function of percent of your HG. Say 10 to 15%, no, yung ating friction head loss. Kaya kung halimbawa, if you are given 10%, no, of your 10% friction head loss, your net head is a function of 0.9 Hg. Now, we have, of course, yung arrow technique natin, no? So, this is the hydraulic turbine. So, ganun pa rin. We can measure or compute our water power. Okay? U gamma H, effective head, and can be converted into brake power and your electrical power output. So, ito pa rin yung ating arrow diagram. We have water power, brake power, and electrical power input. So we can get the relation for mechanical efficiency. We can get the relation for generator efficiency. Okay? Napapakinig niyo ako?
Opo, sir.
Then, of course, ito nga yung ating specific speed. General equation is N square root of HP. No? So usually, ito nga ay brake power. Okay? Brake power or water power if your mechanical efficiency is 100%. No? So, yung head natin, no? Kapag English units, it should be in terms of head. This is effective head or net head. No? And then it should be in terms of meter kapag SI units. Kapag SI units, yung horsepower natin nagiging kilowatts. Okay? Your N is still RPM. So for laminar flow, ito nga yung ating approximate equation. No? Instead of using your Moody chart, you can evaluate your friction factor. No? By knowing your Reynolds number, no, your friction factor is just a function of 64 over Reynolds number. No? Pero kung siya ay turbulent flow, dapat malaman mo yung roughness coefficient, which is based on the pipe material. And for turbulent flow, yung FD natin, yung friction factor, can be taken from your Moody chart or Moody diagram. Okay? So kanina dun sa video, I have shown to you yung Pelton turbine. So we can evaluate now the performance parameters based on the based on the presentation, based on the video. No, kanina meron tayong tinatawag na velocity ng jet, velocity ng bucket. We can have your speed ratio. We can compute for your speed ratio K sub U, which is equal to U over V1. V1 is your velocity of jet, which can be computed from CV, square root of 2dH. CV is basically your jet coefficient. No? Ito naman yung velocity ng wheel natin, which is U, KU times V1 from your speed ratio. Okay? Yun. So U is equal to KU times V1. Ang velocity ng wheel natin. Likewise, we can compute for U by knowing your pi dn over 60. D represents diameter ng wheel natin. Okay? N is your RPM. Okay? Pi dn over 60. So this is basically a tangential velocity. So ganito yung application niya doon sa yung wheel. Tangential. Okay? D represents the diameter ng wheel. Okay? We can compute also your volume flow rate by knowing your area of jet. Area ng jet is pi over 4d squared. D represents, small letter d, represents the diameter of jet. And multiplying your V1, yung velocity ng jet natin. V1 is velocity of jet. No, ito yon, V1. Okay? So, makukompute natin yung volume flow rate. Then, meron tayong tinatawag na ratio of jet diameter to wheel diameter, D over D. Small letter D, diameter ng jet, wheel diameter, big letter D. So, yan yung ratio. And then, overall efficiency, we can compute work ng water power, no, over Q gamma H. Ito, H natin is basically your effective or net head. We can also compute our hydraulic efficiency using equation for your jet velocity and wheel velocity. By knowing your U, your wheel velocity, 2 times U, then we have your velocity ng jet, V1 minus U, okay, times 1 plus cosine P. P represent, nawawala yung P doon, cosine P represents your blade angle. So 1 plus cosine P. So P is your blade angle divided by V1 squared. Sabi dito, theoretically, the jet deflected through 180 degrees and therefore your angle P is equal to 0 degree. Yan yung ating performance parameters kapag ka Pelton turbine. Na-receive ninyo yung kopya?
Yes po, sir. Na-send ko na po sa
Okay, so meron tayo ditong solve problems. Okay, so here, paki-correct nito, this is available head instead of area. This is available head, H. No? 28 meters. No? Available head, the available area. Catchment area is 42 square kilometer. Your rainfall is 140 centimeter per year. Percentage of total rainfall utilized is 68%. Kaya from here, you can compute your volume flow rate. No, kasi dito sa rainfall natin manggagaling yung amount ng water. And stock efficiency, turbine efficiency, generator efficiency, and load factor. First, you have to calculate the power developed, the water power. The second is you are going to suggest or select suitable machine. When we speak of suitable machine, we are referring on the type of hydraulic turbine that can be used given these conditions. Okay? So yan, meron ditong solution. Okay, paki-check ninyo. So I repeat, paki-correct available head instead of available area. No? Bless you, bless you. Then you have your dito, meron tayong quantity. Doon sa number 2, this is almost the same. Okay? Pareho yung problem niya. Okay, paki-check. Quantity of water. Quantity of water available. Riha, paki-correct na riha. Quantity of water, it should be quantity, hindi not quality. No? The quantity of water, nakikita ninyo, hence the quantity of water available per second. This one. Quantity, not quality. Okay, okay, correct na. So you re-evaluate here, this one, no? Ako lang ay pupunta doon sa steer hub at hindi pa kami tapos doon sa chat evaluation. Then later, continue tayo kasi meron pa naman tayong klase mamayang 5, no? Continue natin, i-discuss pa rin tayo later. Okay? So yan, i-re-evaluate muna ninyo yan and then 5 o'clock we will resume, no? So pwede kayong mag-leave, then later 5 or even 5:30 pwede tayo mag-resume. Okay? I-chat ko si Justin.